Welcome to Chapter 9, Part 3. This corresponds to slides 53 to 72 in the PowerPoint slides, and it will be on Chapter 9 lecture worksheet, pages 5 through 9. So last time we left off, we were talking about drawing kind of simple Lewis structures. Lewis structures for neutral molecules and Lewis structures for polyatomics. But all of the Lewis structures that we talked about thus far have followed the octet rule. So today we're going to look at Lewis structures that don't follow the octet rule, and then using formal charge and resonance to figure out, which Lewis structure might be the best one if there's more than one possible Lewis structure that we can draw. I want to emphasize, though, in Chapter 9, you really need to do the lecture worksheet problems. I've provided them for you so that you get lots and lots of practice on drawing Lewis structures. That is the only way that you will get good at drawing Lewis structures, is to continually practice them until you can draw them in your sleep. So make sure that you are going through and doing all those lecture worksheets. I know it's a lot of problems, but the reason that there are a lot of problems is because, you need the practice. So I just wanted to emphasize that, really put that out there. That's why these Chapter 9 lectures are shorter, and we're spreading it out over longer time, because I want you to go through and actually do all of those practice problems. So, some exceptions to the octet rule. We talked about beryllium and boron last time. Beryllium will share 2 electrons and it will form 2 single bonds. So that means that it will end up with only 4 valence electrons. Similarly, boron will share its 3 electrons to form 3 single bonds. So it will end up with 6 valence electrons. So these 2 atoms will commonly have less than 8 valence electrons around them. So they're not following the duet rule like hydrogen and helium, but they're not following the octet rule like most other elements. They're kind of doing their own thing, which makes them very, very reactive because they do have less than 8 valence electrons. So elements in period 3 and below can expand their octets by using these empty d orbitals. So we know, if we think about the d block when we were writing valence or electron configurations, we had 1s and then 2s and 2p, 3s, 3p, 4s, 3d, right? And the d block starts in that third energy level. So this is why elements that are in that third row, that third period, can access those empty d orbitals and can put some electrons in there to expand their octets. That's kind of the most we're going to get into, the rationale in this class. Higher levels of chemistry, we'll talk to you lots more about it. Some molecules, though, so rather than, having less than an octet or expanding their octet, some molecules can have odd numbers of valence electrons. So this is like nitrogen monoxide here. If you look at nitrogen, this nitrogen only has a single electron on the nitrogen. So if we're counting up valence electrons around the nitrogen, we have 1, 2, 3, 4, 5, 6, 7. And right now, nitrogen does not have a complete octet. It only has 7 valence electrons. In addition, it has this 1 electron by itself, which is really unusual. And so whenever a compound or a molecule has an electron by itself like this, we call it a radical. This is a special type of chemistry that it can do. We're going to look at drawing some radicals. This is, like I said, this is really unusual that these compounds do this, so don't go around making radicals all the time. But if it's the only way to draw the Lewis structure, then that will be what you draw. But they're very reactive compounds, and they do some really cool chemistry. So, some molecules like SF6 and PCl5 have more than 8 electrons around the central atom in their Lewis structure. So this is what they look like. So the one on the left, that's SF6, and the one on the right is PCl5. So if we look at SF6 here, we've got, if we're looking at our sulfur has 2, 4, 6, 8, 10, 12 electrons around the central atom, which is way more than 8, which we are normally allowed. And again, phosphorus over here on this side is 2, 4, 6, 8, 10 electrons around the central atom. Again, more than 8 like we're normally allowed. The fluorines and the chlorines are obeying the octet rule, and typically this will be true for these peripheral atoms. So atoms that are bonded to the central atom will typically follow the octet rule. It's kind of unusual that a peripheral atom will break the octet rule. It'll just be these central atoms that sometimes can have more bonds or can have more electrons than 8. So our rationale here is that they can violate the octet rule through the use of the empty d orbitals. Both sulfur and phosphorus can utilize empty d orbitals to hold pairs of electrons that help bond those halogens. So again, this will pretty much just be for the central atom. And like I stated in the last lecture, usually if there is a way that you can draw the Lewis structure to obey the octet rule, that's a good way to go. But if the only way you can, draw the compound, right, like, SF6, fluorines can only make one bond, and fluorines can't expand their octets. The only way to draw SF6 is the way that it's drawn here, is to bond all 6 of those fluorines to the central atom. So in that case, then it's okay to break, the octet rule, because there's no other way to draw the compound. So resonance is something that you probably haven't talked about before, but resonance is invoked when more than one valid Lewis structure can be drawn for a particular molecule. So this is benzene, C6H6. It's a really pretty liquid. It's super carcinogenic, but it's really, really pretty. And it smells kind of nice. So if you come across it in the lab, it kind of shimmers and looks cool. But on a molecular structure, the way that we draw benzene, and so these, like we've talked about before in this class, anytime there's an intersection, these are all carbons. Okay, this would be like how you would draw it in organic chemistry. But there are 2 different ways to draw this particular compound. You can draw it the way that we have here on the left, where we go, single and then double, and then single and then double, and then single and then double, or the way we have it on the right, where it's double, single, right? So they're the double bonds have moved essentially around it. And so the actual structure is an average of these resonance structures. It's not really like the structure on the left. It's not really like the structure on the right. It kind of falls somewhere in between. It's an average. So instead of having single bonds and double bonds, you can think of them as all being like 1.5 bonds. All of the bond lengths in the ring are identical. Even though we have them drawn as alternating single and double bonds, when we look at this using spectroscopy, all of these bond lengths are identical. We can't see single bonds and double bonds. All of the bonds kind of end up being 1.5 bond. It's like an average between these 2 structures. Whereas like here, this is drawn as a double bond, and here, this is drawn as a single bond, right? And so, averaging these 2 structures, instead, all of the bond lengths kind of look like 1.5 bonds. They're somewhere between a single and a double bond. So it's not like the structure on the left, it's not like the structure on the right, it's somewhere between the 2. So this is what resonance is, when we can draw more than one Lewis structure for a given compound. So we talked about bond length and bond strength last time, and I use this term multiplicity, right? Which just means more compound or more bonds between the elements. So if we look at the carbon-carbon single bond versus the carbon-carbon double bond, right? We see that the double bond is shorter and the double bond is stronger, right? So as multiplicity increases, right, going from single to double, we get shorter bonds and stronger bonds. If we then look, double to triple, we get even shorter and even stronger bonds. So as, the number of bonds between the elements increases, as multiplicity increases, the bonds become shorter and the bonds become stronger. Okay, so that's why when we were looking at this benzene on the last one, we can use spectroscopy. We can see that the bond length is somewhere between the bond length of a single bond and a bond length of a double bond. It's not, as long as a single bond. It's not as short as a double bond, but it's somewhere in between. Okay, it's between a single and a double bond. So resonance bonds are stronger and shorter than single bonds, but they are longer and weaker than double bonds. Again, like I was saying, you can kind of think of them, since it's a double bond here and a single bond here, you can think of it as kind of being like a 1.5 bond, but it would be a 1.5 bond for every single carbon-carbon bond in this molecule. Similarly, if we think about ozone, so here's ozone. You guys have heard about ozone out in the atmosphere and things like that. There are two different ways to draw the structure of ozone. We can draw it with the double bond on the left, or we can draw it with the double bond on the right. Both structures obey the octet rule for all of the atoms. All of the oxygen atoms have 8 valence electrons in both structures. And so that leads us to, which one is right? Well, neither one is right? Instead, it's a hybrid. It's kind of between these two different structures. So instead of this being, a double bond and a single bond, or a single bond and a double bond, all of these bonds end up kind of looking like a 1.5 bond. They're somewhere between a single bond and a double bond, because in one resonance structure, it's a double. The other resonance structure, it's a single. And again, neither structure is correct. Our actual structure kind of falls somewhere between this. It's a hybrid of them. So we also have resonance in polyatomic ions. So we talked about how to draw these Lewis structures for polyatomic ions last time. I'm going to assume that you are all good students and went and practiced it a lot. So one way that we could draw the resonance, or the Lewis structure for carbonate, is this one on the left, right? We could make the double bond to the oxygen go up. But like I talked about in the last set of slides, it doesn't matter which oxygen we had chosen to double bond, right? Which oxygen we had chosen to share one of its lone pairs with carbon. So we could have picked the one, on the bottom left, like the middle structure, or the one on the bottom right, like the far right structure. And again, none of these structures is correct. None of them's wrong, really, but none of them are completely correct. In essence, it's going to be a hybrid of, all three of these. So now, though, instead of it being, just a double versus a single bond, we've got, if we're thinking about this one, we've got a double versus a single, essentially. So I would think of this as being, like a 1 1/3 bond. If we were looking at comparing it, where it's still longer and, it's still shorter and stronger than a single bond, but longer and weaker than a double bond. But it's going to end up a little more like a single bond than a double bond, because we have 2 resonance structures that have single bonds and only one with a double bond. But again, all of these bonds in this molecule are actually identical. None of them is a double bond, none of them is a single bond. They all end up kind of being a 1 1/3 bond. Similarly, if we look at acetate, here's how we would draw that acetate ion, right? And it wouldn't matter which one of those hydrogens we chose to double bond, which one of those oxygens we chose to double bond with the carbon. But in one of the structures, it's a double bond, and the other one, it's a single bond. So in reality, right, it kind of falls somewhere between a single and double bond. So this is what resonance is. If you were to write the resonance structure for nitrate, the way that you would do it is to first write one Lewis structure. Draw one really solid Lewis structure that follows the octet rule, has the right number of electrons and things like that. And usually you'll get to the point, when we drew this in the last PowerPoint, we got to this point, where all of our oxygens had 8 valence electrons, but our nitrogen did not have an octet yet. And so nitrogen only had 6, all the oxygens had 8, so we picked one of the oxygens. We said, okay, this one on the bottom left, it's going to move those electrons, and it's going to share them with nitrogen. And so instead of being drawn where nitrogen only has 6, now we can draw it like this, where oxygen is now sharing those pairs of electrons. Just that one, though, and the other ones we left alone. So now all of the oxygens have 8, and the nitrogen also has 8. So back on this step, right? This is kind of how I would use, or how I would think about drawing Lewis structures. It didn't matter which one of those oxygens I picked to donate electrons to share with nitrogen. So I picked the one on the bottom left, but in my next resonance structure, like, this one, maybe I picked the one on the top to donate those electrons. And on this far one, I picked the one on the bottom right to donate those electrons. That's how you would go about generating these different resonance structures. So again, though, none of them is quite correct. None of them, again, are wrong, but none of them are quite correct. Instead, the actual structure is kind of a hybrid in between all of these. There are instances where, like in this last slide, all of those resonance structures were fairly similar, right? They just differed by which electron or which oxygen we chose to donate electrons to double bond with that nitrogen. But sometimes the Lewis structures won't be so identical. And sometimes one of the resonance structures, is better than the other resonance structures. So we need some criteria for picking which resonance structure is the best, which one's the most important resonance structure, which one contributes the most to the real structure. So this is kind of in order of importance. So our first criteria would be we want really small formal charges. Doesn't matter if they are positive or negative, but we just want small numbers. Like zeros are really great. And if we can't have zeros, then we want like +1s or -1s over +2s and -2s, right? So you want smaller numbers. Doesn't matter positive or negative. We just want small numbers. And then after that, we want the more negative formal charge should exist on the atom with a larger electronegativity value. And rather than continually pulling up your table of electronegativities, just remember that fluorine is the most electronegative atom. So usually a good rule of thumb is whichever atom is the closest to fluorine, that one should bear the negative formal charge. So we want to put the negative formal charge on the most electronegative atom. And then if that's still, if you're still trying to, rule out which one's the best, you want to get unlike charges as close together as possible. So if you have a positive and a negative, you want to sit them right next to each other in the atom. And then, similarly, if you have two positives or two negatives, you want to put them as far apart as you can in this molecule. Usually, though, these first two rules will solve, 99% of your problems. The last two rules are just, if you have really similar structures, you're having a hard time choosing between them. So we're going to go through some examples. But first, we must figure out how to calculate formal charge. So the way that we calculate formal charge is we do our number of valence electrons. So the number of valence electrons that normally belongs to that atom. So like nitrogen is 5, oxygen is 6, fluorine is 7, and so forth. And then you're going to subtract out the number of bonds that are going to that atom. And then you're going to subtract out the number of unshared electrons. And this is total. So like a lone pair counts as 2 unshared electrons. You need to know this, formula, if you want to think about it that way. You need to know this formula or this way of calculating formal charge because it will allow you to pick between Lewis structures. I won't be providing this for you, but you are going to get a lot of practice. So number of valence electrons minus the number of bonds minus the number of unshared electrons. So here's an example. Let's go through and calculate the formal charge for each atom in this Lewis structure. So if we think about hydrogen, neutral hydrogen has 1 valence electron just like normally, and it shares 1 bond with oxygen. It has no unshared electrons. There's no like lone pairs. So the formal charge of hydrogen is 0 because we take that 1, we subtract out the bond, we subtract out no valence electrons, or no, unshared electrons, and we get 0. So when we're, normally we'll go through these structures and we will write the formal charges on the atoms. You do not have to write zeros though, that's redundant. So if we look at this oxygen, normally oxygen has 6 valence electrons. And right now this oxygen is forming 2 bonds. It's got 1 going to hydrogen, 1 going to nitrogen. And it has 4 unshared electrons, right? 2 on the top 2 on the bottom. So the formal charge on this oxygen is 0 because we took 6, right? Our 6 electrons, we subtracted our 2 bonds, we subtracted our 4 unpaired electrons, we get 0. Let's try another one. This oxygen, it has, 6 electrons. It forms 2 bonds. Both are going to the nitrogen. It has 4 unshared electrons, and the formal charge will be 0. So again, we've got 6 minus 2, those 2 bonds, minus the 4 unshared electrons. That will get us 0. This neutral oxygen normally has 6, just like we've had before. This oxygen is only forming 1 bond, unlike the other ones that are forming 2. And it has 6 unshared electrons, unlike the other ones that only had 4. So the formal charge on this oxygen is -1. So when we go through and calculate this, we had the 6, we subtract the 1 bond, we subtract the 6 unbonded electrons, and we get an overall charge of -1. So that's why this negative is here. Because that is the formal charge. That's usually how we'll write it. We'll just put it as close to that oxygen as we can. So now going through and calculating the formal charge on nitrogen. Normally nitrogen has 5 electrons. Right now this nitrogen has 4 bonds going to it. There are 2 going to the top right oxygen, 1 going to the left, and then 1 going down. It has no unshared electrons. There's no lone pair sitting on that nitrogen. So that our formal charge is +1. We took our 5, we subtract our 4 bonds, no unpaired electrons, and we get a +1. So we put a positive next to the nitrogen. So we've got our positive here on the nitrogen, our negative here on the oxygen. And if we were to look, and make sure that this is a really good Lewis structure, right? Oxygen is more electronegative than nitrogen. So it's a good thing that oxygen is the one that's bearing that negative formal charge. Nitrogen is more electropositive, so it will bear the positive formal charge. So this is a pretty good Lewis structure. Oh, also, the positive and the negative, they are right next to each other, which is also a good thing. So technically, a Lewis structure is not complete unless formal charges, if any, are shown. If I'm asking you to choose between Lewis structures, you always need to write out the formal charges and tell me what they are. Most times, and especially when you get to higher levels of chemistry, these formal charges will always be shown on molecules. So this is a really good habit to start getting into. I know it's kind of a pain to go through and calculate all of the formal charges, but you'll start to recognize some patterns. Like anytime oxygen only has 1 bond going to it, like this bottom oxygen, it will always have a negative formal charge. Anytime nitrogen's got 4 bonds going to it like that, it will always have a positive formal charge. And you'll start to notice these patterns the more and more that you do this. So if we went through and we calculated the formal charges on this atom, we don't need to go through and calculate the formal charges on hydrogen because hydrogen will always be a 0. Hydrogen can't make more than 1 bond, so as long as it's just forming a single bond like it is in this ammonium on the side, you don't need to go through and calculate the formal charges of hydrogen. But nitrogen has 5 valence electrons normally. We subtract out the 4 bonds. There are no unbonded electrons. So we get a +1 formal charge on nitrogen. So that's why that positive here, it should be sitting closer to the nitrogen. It's just hard to make it do that. The fluorine's a halogen, so halogens typically make 1 bond. So I don't usually go through and calculate formal charges on these peripheral halogens because as long as they are making 1 bond, they have a formal charge of 0. Things that are following the honk rule, right, that we talked about last time, if you have something that's following the honk rule, it has a formal charge of 0. It's just when it starts to break this honk rule that things get interesting. So boron, in the middle there, boron normally has 3 valence electrons. So we subtract out our 4 bonds. We have no unbonded electrons, so we have an overall -1 formal charge. So that's why there's a negative there on boron. What I want you to try is go through and draw this formal charge, or this isocyanate, NCO. There are 3 possible resonance structures, and you're going to draw them in that order: nitrogen, carbon, oxygen. So carbon will go in the middle, and a nitrogen on one side and an oxygen on the other. There are 3 possible resonance structures that you can draw, and then I want you to go through, so in each one of those 3 resonance structures, go through and draw and calculate the formal charge on each of those atoms. And then once you've gone through and figured out, so you'll end up with 9 formal charges. And once you've done that, use those rules then to figure out which resonance structure is the best. And so when we say the best, it means which resonance structure is contributing the most to the overall resonance hybrid, the overall true structure. So go ahead and pause here and try that out. Hopefully these are the 3 resonance structures that you drew. So you have, nitrogen and carbon and oxygen. So there's one way you can draw it with a single bond going to the nitrogen, triple to the oxygen. There's double to both, which is option B, and then option C would be a triple bond to nitrogen and a single bond to the oxygen. You should have gone through and figured out which, all of the formal charges on all of these atoms. So if you did that, you would get -2, 0, +1, -1, 0, 0, and 0, 0, -1. And so immediately we can rule out option A. Option A is the only one that has a really large formal charge here, that -2. And again, we want to always minimize formal charges. So since option A has a -2, option A is no good. So then if we compare option B and C, right, they both have 2 zeros and a -1. And so then we need to figure out, okay, so where should the negative go? So the negative is always going to go on the most electronegative atom. So if we look at our periodic table, we would see that oxygen is more electronegative than nitrogen. So since oxygen is more electronegative, it should bear the negative charge. So our answer is C. So I have all of that rationale on this page here. Here's all of the formal charges. There we go. So like I said, forms 2 and 3, or B and C, have smaller formal charges. And then once we get to those, you want the negative on the most electronegative atom, which again should be oxygen. So that's it. That's all for this set of slides. Again, you need to go through and keep practicing drawing your Lewis structures. Do all of the lecture worksheet problems and then find more of them. Do the problems out of the textbook, do the problems on the study guide, draw as many Lewis structures as you can, because like I said, as we move farther and farther into the course, I'm going to assume that you can do these, and I'm going to assume that you are good at them. So keep practicing, and as always, send me any questions that you have.